In this section of the course, we're going to be taking a look at internal forces. The learning outcomes will be to compute the internal forces in beams, construct shear force and bending moment diagrams, and write shear force and bending moment equations. But before we move on to shear force and bending moments, we first of all need to understand what a shear force is. So, we have this diagram here. We have four types of internal forces that we generally encounter. The one that we're most familiar with is axial forces. We've seen that in trusses. So where we have a piece of material, here, and we've subjected this material to two forces pulling on that piece of material, and as a result of that pulling, the piece of material stretches, so the original shape would have been something like this, and will have also, due to something called Poisson's ratio, which we'll discuss in strength materials, will have also got thinner as a result. That's true for most materials, but not all. Okay, then the second type of internal force we have is that which is called a shear force. So here we have again a piece of material, and we have forces on either side of the block of material, one pointing up on the left-hand side, pointing down on the right-hand side. And as a result of these forces being applied, the original block has transformed from a square block to a trapezoidal block. And this is what we call shear force. Then we move on, we have what's known as bending. So again, we have our same block of material. We're applying a clockwise moment on the left-hand side, an anti-clockwise moment on the right-hand side, and as a result of that, our square block changes. So now we have this curvature in the material, and you can see that the material is stretched at the bottom, so the bottom will be in tension, and we'll have got shorter at the top, so the top of the material will be in compression. And finally, we have a fourth type of internal force, and now we have a block. We have to draw this now in 3D. So we have a cubic block, a cuboid, and now we've applied two equal but opposite moments, but these are moments out of plane. So if we imagine a dotted line go through this material, the moment is going around that dotted line, so around this dotted line. And as a result of this twisting motion, the piece of material gets twisted. This gets really important, especially in mechanical engineering, where we have torsion of shafts. Can be also a problem in petroleum engineering, where we have twisting of drills that are down boreholes. Okay, so those are the four types of internal forces. In this section of the course, we're really going to concern ourselves with shear and bending, which we use a lot. But before we move on to shear and bending, we're going to have a quick look at actual internal forces. So, what we need to do first is understand what actually is an internal force. So here we have a bar which is 8 meters long, and we have a series of forces along this bar, and what we'd like to know is what is the internal force at a distance x equals 4 meters from the left hand side. Okay, so to the left of this point that we're interested in, we have a 1 kilonewton force, a 0.5 kilonewton force, a 2 kilonewton force, a 1.5 kilonewton force, and we add all of those up, and the sum of all of those forces is 5 kilonewtons. On the right hand side, we have 2 kilonewtons, 2 kilonewtons, 1 kilonewton, and the sum of all of those forces is again 5 kilonewtons. So at the point in the middle at 4 meters, we want to know what is the internal force. And there are three potential answers that we might think of. Because we have 5 kilonewtons applied at either side, the internal force we might think of as 5 kilonewtons, we might think we have 5 kilonewtons pulling one way, 5 kilonewtons pulling the other, so the total force could be 10 kilonewtons, or because we have 5 kilonewtons and 5 kilonewtons, that the piece of material is in equilibrium and therefore the internal force is 0. So we have to really define what we mean by internal force. And so what we need to do is imagine we have a piece of material at this point, x equals 4 meters, and what we're really interested in, like the diagram we've drawn above, is what are the equal and opposite forces on this piece of material, and that then is the internal force. So in the case of birth, we have 5 kilonewtons and 5 kilonewtons, and so we consider the internal force to indeed be 5 kilonewtons. And the other way we can think of how we do this is we can use, like in trusses where we had a method of sections, we use the method of sections and we can apply a cut wherever we want to identify our internal forces, and where we make that cut, the force that we require, FL in this free body diagram for the left hand side, that FL is the internal force that must be coming from the material and acting on the left hand side. Likewise, we draw the free body diagram of the right hand side piece of material, and again this FR is the internal force in the material that is keeping the right hand side of the bar in equilibrium. And we'll use this concept all the time in getting either axial force diagrams, shear force diagrams, or bending moment diagrams. And so just as a sneak preview of how we're going to go with the rest of this section of the course, we can imagine we have a beam, and this beam maybe is simply supported, so pin supported on the left hand side, roller supported on the right hand side, and maybe it's subject to some load. Maybe it's got some point load P and a UDL, a uniformly distributed load. Let's call that little w, some people might call it omega. Again, we've got some dimensions on there, and we might be interested to know what is the shear force at this point and what is the bending moment at this point. And the procedure we're going to apply every time is like above for the actual loads. So for a shear force, what we'll do is we'll make a cut at the point we're interested in, and we'll cut our beam, and we'll draw a free body diagram of the beam section we've got, and we'll work out what is, so this is P, this, if we call this A, this B, so RAX, or so RAY, RAX, RAX, then we will work out what is the force we need to come from the material, the shear force in the material, that will keep this left hand side of the beam in equilibrium. We can also work from the right hand side as well. And likewise, if we're worried about bending, we'll draw a free body diagram of the entire section. Again, we have the reaction forces on this section, we have the external load, we still have the shear force, and we could also have a moment here. And what we'll do is we'll take moments from the point we're interested in to work out what this moment would need to be to keep the section in equilibrium. And also, we don't need to consider the shear force in that moment, because the shear force will be going straight through the point where we're taking moments and therefore has no lever arm. But we'll come on to these examples as we go along. So before we head off into looking at shear forces and shear force diagrams, we're going to just have one look at what is the difference between a force and an internal force. And so it's kind of hinted at in the diagram above, but let's draw a block of material and we'll have a look at the actual force first of all. So if we were to apply a single force F on the right hand side, then as a result of this single force F on the right hand side, all that would happen is that the block would shift a small distance to the right hand side, and or even could go into dynamic motion. So a single force alone will only cause a rigid body movement of a piece of material. Now, if we apply two forces, then the piece of material will find itself getting stretched. So as we've drawn above, now that piece of material will elongate as a result of the two forces applied. The two forces need to be equal and opposite for it to remain in static equilibrium. But as a result of applying the forces now, we have a new shape of the body, a stretched body, and it's the action of the two forces at either end of the body that gives rise to an internal force in the body. And as we'll see in strength of materials, gives rise to stresses and strains in the body. So take the same situation again, same block of material. And now if we apply just a force on the left hand side, all that this will do is cause the block to rotate, especially if we fix it at some point. It will just cause the block to rotate, but it won't have any change in its shape whatsoever. So we'll still have the block in exactly the same dimensions, no stresses or strains as a result, just pure rigid body motion. Whereas if we have the block of material, I can take away this force now, if we have two forces going in the same direction, again the block will just move upwards. However, if we have the situation where we apply a force going downwards on the right hand side, this causes the block to make that trapezoidal shape, which is causing stresses and strains within the block. So this, and we'll call this V, this is generally used for shear force, this shearing of the block, this changing of the shape from this original rectangular shape to a trapezoidal shape is called shearing. And again, we'll have a look finally at the other one that occurs in 2D, which is bending. And if we apply a moment to this block, all that will happen is this block will spin around and around in circles. The block will keep its dimensions, so there'll be no change of shape to the block. However, if we now apply an equal but opposite moment, and we tend to use M, which is kind of confusing. We use M for moments and M for bending moments, where we have the two moments. This will now cause the block to change its shape. So the difference between a force and an internal force, a shear force, or moment and bending moment, is that the internal force or bending moment is the action of two forces or two moments on the body to create some deformation in the body.